We have learnt about Oersted's discovery that an electric current produces a magnetic field. But since the discovery was made, attempts were made to observe the reverse effect. Can electric current be produced by magnetic field? In the year 1831, the great English physicist Michael Faraday discovered just that. He showed that whenever there is a change in the magnetic lines of force around a coil, then current is produced in the circuit. So if we move this bar magnet inwards or outwards, there will be current induced in the coil. Understand this well. Only a change in the magnetic lines of force. So if we just hold a stationary magnet around or inside the coil, then there will be no current in the circuit. But when the magnet is moved, the current will be produced. But how long do you think the current will last? It's pretty logical. The current lasts as long as there is change in the magnetic lines of force. Magnet moving, current is induced. Magnet stops, no current flow. He named that phenomena as electromagnetic induction. Electromagnetic induction? Sounds intimidating, right? It won't if you just understand the three parts: electro, magnetic, and induction. The last part is induction. What exactly is induced? It's current or electric current. That's what electro stands for. And the current is induced because of what? Yes, changing magnetic field lines. That's what magnetic stands for. Hopefully the name doesn't sound that scary now. By the way, how do we know that a current is induced in the circuit? This device called a galvanometer helps us detect the presence of current. What is a galvanometer? It's a sensitive device used to detect small currents. It also gives us an idea about the direction of current. If the current is moving in this direction, then the galvanometer will move towards the right, and then when the current flows in the opposite direction, it will move towards the left. Also, how did Michael Faraday discover the concept of electromagnetic induction? After connecting the conductor with the galvanometer, he took a bar magnet and moved it towards the coil. To his surprise, the galvanometer needle was deflected. That's when he discovered it. And just to be sure, he tried it again. What else did he observe? He observed that when he took the magnet towards the coil, the galvanometer got deflected to one side. And when he took it away from the coil, the galvanometer deflected to the other side. Interesting, right? And when he kept the magnet stationary near the coil, there was no deflection in the galvanometer at all. So he concluded that a current is induced only when the magnet is moved towards or away from the coil. It happens because the magnetic lines of force are changing. But how? Let's picturize it. When he brought the magnet close to the coil, you notice that the lines of force passing through the coil increases, right? And when you move it away, it reduces. In either case, the number of magnetic lines of force is changing, which is why the current is induced. And what about the case when the magnet was stationary? In that case, the number of lines of force passing through that coil will not change. Hence, there will be no current induced in the coil. Let me ask you a few more questions. What if I'm taking the coil towards the magnet? Will current get induced? Also, what are the factors which affect the strength of the induced current? Move to our next video to find out the answers.